All right, so this lecture will be divided into two parts. First, I will talk about traffic safety applications. So this is one of the 4 application areas that you should choose for your project. So the third part of the project consists of analyzing a certain ICT application from a communications perspective, what are the requirements and so forth. So there's been guest lectures on e-health, power engineering or power grid, smart grid if you like, and process control, and this one would then deal with traffic safety. So the other 3 people that have been giving these lectures are people in the field. I happen to have done quite a lot of research on this also, so well, I don't know, I consider myself a little bit knowledgeable, maybe not super expert, but anyways, well, I'm an expert, let's go with that. So traffic safety, what is that all about? Well, we all drive around in cars, buses, trucks and whatever, and we would like to arrive at the destination safe and sound. So the reason why we are interested in this is quite simple. It's this number here. So do you guys know what this could be? Yeah, so these are the number of people that are killed in road accidents every year globally, like 1.3 million. That's quite a lot of people actually, compared to other calamities, right? Like war and pandemics and other things, right? So this is quite a serious problem. Now, not all of these are killed inside the vehicle. It could be pedestrians that are hit or bicyclists and so forth. So something needs to be done about this. And if one wants to read a little bit more about what traffic safety is all about and why it's important, there is this study by the World Health Organization. So it's a link there if you want to follow that. So anyways, this is a serious problem for many reasons. Of course, from the human suffering of injuries and deaths and so forth. It's tremendous cost for society and yeah, and so it's not good, right? So what can we do about that? Well, I claim that part of the solution is ICT, information and communication technologies, and communications. And in particular, today we will talk about V2X communications, vehicular to anything communications. So what is this all about? Well, it's about enabling certain applications called Cooperative Intelligent Transport Systems. So this is a term which is used in the literature and in the discussion. So ITS, Intelligent Transport Systems, been around for a long time. So the key word here is cooperative. That's the new thing. And cooperative means that we are doing V2X communications. Okay, so what are these type of applications then? Well, we can broadly divide them into 2 parts, traffic safety and traffic efficiency. And traffic safety is what it is, right? It's sort of self-explaining. It's to avoid accidents. So, for instance, if we have a situation like this, the blue car is trying to make a left-hand turn here, so it's flashing its indicators here. And there is a two-wheeler, maybe like a scooter or something like that, approaching this crossing. The line of sight of the driver of the scooter here is blocked by this truck. So here's a potential dangerous situation. I mean, this car can drive out and then it's be hit by the two-wheeler here. It's quite a common type of accident. It's pretty bad for the driver of the scooter. So what can we do about that? Well, if this car is then sending information indicated by these blue rings here, indicating that it's a car, it's at this X and Y coordinates, is trying to make a left-hand turn, then this information can be interpreted by an application in the scooter to warn the scooter driver about, okay, there is a potentially dangerous situation here. and then the scooter driver can then take action to avoid the accident. Or if the scooter driver is not making any missed the warning or whatever, when the collision is imminent or more or less, if the driver doesn't do anything, the scooter itself can do something. Maybe turn off the engine, maybe brake. I mean, it's a little bit hard to have automatic steering on a scooter, right? That would be probably as bad as driving into the blue car here. But anyways, if this would be a car, one could also do steering and things like that. So there is a whole progression of things one could do if one has the information. And V2X makes sure that actors or agents, if you like, in this traffic situation can make intelligent decisions. And the C here in cooperative means that by sharing information, we can the different vehicles can cooperate in trying to solve this situation. Traffic efficiency, on the other hand, is basically to use roads better. Okay, to use the infrastructure in a better way, so we don't have to build new infrastructure when traffic demands goes up, and also to reduce fuel consumption, reduce exhaust emissions, all kinds of things. So think of this as being green, if you like. So there's safe and green. That's what we would like the transport to be. So there are many different applications here, and one application which is under discussion quite a lot is this what's called platooning, where vehicles drive very close to each other to reduce the air drag, for instance, which means that fuel consumption goes down, exhaust emissions goes down also. And what is more, another advantage of this is that we can squeeze in more traffic for the same road segment, for the same road. We don't need to build another lane to support more traffic. And this is a super good thing, right? Because we know that road infrastructure, there is never an end to how much roads you need because traffic demands is increasing. So if we can use the infrastructure in a smarter way and still and also save on carbon emissions and things like that, that's great, right? Okay, so what is then V2X communication was the enabler here. So what is a V? Well, V is a vehicle. So of course it's personal cars, but it's for sure buses and trucks as well. And then there is a fourth category that one might not think is so much about, and that's construction equipment. These are also, safety issues here for sure. There happens accidents every year where people are injured or killed by these vehicles. And also, if one can use them in a more efficient way, we can save on fuel and exhaust and all these things, right? So when it comes to automated driving, for instance, maybe these type of vehicles will be the first types that would be automated because they drive in a confined environment. There's a lot of regulations around this also. So one should not forget about this segment also. Now, it happens to that all these vehicles here are Volvo products. You might guess why that is the case, but this is of course not Volvo specific. This applies to any vehicle manufacturer in the world, I would say. Okay, X then. So this is a vehicle. What is X? Well, X could be another vehicle. It could be road infrastructure or this vulnerable road user, VRU. So what are those? Well, if we think about... is this not working? Okay, so here's a road infrastructure. It's gantry here, where you have speed advisories here that people are supposed to follow and do to some degree at least. So you can change these speed limits adaptively to maximize the traffic flow over that segment. And actually, it's sometimes better to reduce the speed to increase flow over a segment. So driving at maximum speed is not always the best one. So this, of course, is then updated adaptively, which means there needs to be communication to this. We could have other things also, like ordinary stupid infrastructure is also important to communicate with. Here, the vehicles can know when the light is turning green and adapt its speed into an intersection. And particularly if you have heavy transport, you don't want big vehicles to brake and then accelerate, brake and accelerate. So a lot of energy waste and also increased exhaust fumes inside cities and so forth. So if one can simply, the infrastructure you could basically tell us, well, I'm planning to turn red in 20 seconds, and then the traffic can adapt to this. And vulnerable road users is these type of people, and pedestrians and also bicyclists and so forth. And here you see a typical problem with in modern day society. People are not paying attention to where they're walking, right? Maybe plugged in also so they don't hear the traffic around them also. So that could be potentially a dangerous situation. Okay, so what is the state of the art for V2X communications? There are a number of systems which have been standardized but not yet fully deployed, I would say, or not deployed, only in small scale. There are two types of main systems, something called ITS-G5 and something called DSRC. The ITS-G5 is a European standard and DSRC is like a US standard. It's not super important to remember the names here, but what we should remember is that the medium access layer, so this is part of the data link layer, and the physical layer of these type of systems is based on IEEE 802.11p. For you who know this, you recognize that 802.11 is the family of Wi-Fi standards. So this is essentially a modified Wi-Fi system. The upper layers, the network layer, application layer, so forth, are different in the two systems here, but the lower layers are the same. So at least that's good, because we would like to have one system which is global, right? Because you sell vehicles over a global market, and you don't want to have special equipment for the US and for the Europe and Asia and whatever. You would like to have the same thing. But anyways, the upper layers here are basically software defined. So one could think of this, we could potentially write a little bit new software, and we can still reuse the equipment which is mounted in the vehicles if we go this route. Okay, so what is the difference between these systems and Wi-Fi? Well, I would say that the only main difference between 11p and regular Wi-Fi is that 11p allows for what's communication, which is in the language of this standard is called outside the context of a BSS, which is of course completely incomprehensible for the outsider. But what it means, and when we talk about Wi-Fi, we will talk more about this later on in the course, it removes the delay which is incurred by joining a BSS. So basically, when you get into a system, you open your laptop, or when you get to a place and you open your laptop, you're asked for logging on to a Wi-Fi network. You provide your passport and then you log on to that network. So you do that typically once, and when the second time you get into this area, you open up your laptop, you automatically attach to the network, right? But this attachment to the network takes 1 second, 2 seconds, maybe even more than this. And that delay is sometimes not acceptable in these applications. So this means basically that we can communicate over this system without logging on to a network. That is what this meant by this. And we will talk a little bit more about what a BSS is and all these things when we talk about Wi-Fi later in the course. The physical layer of this is OFDM, which is basically what we use in Wi-Fi today. There are many different file layers in the Wi-Fi standard, in the 802.11 standard, but there is only one which is used today, as far as I know at least, and that's OFDM with 10 megahertz channel spacing option. Regular Wi-Fi typically use 20 megahertz here, so there's a small difference there. And here's maybe an important consequence of this, is that the overall data rate, which needs to be shared by all vehicles, all communicating entities within radio range, is 6 megabits per second. So if there's 100 transmitters, they need to share these 6 megabits per second, right? So the data rate per transmitter could be significantly lower than 6 megabits per second. I mean, if there's two sharing this, is 3 megabits per second in the best possible scenario. If there is 4, there's 6 divided by 4 and so forth. And that actually turns out to be a limitation of the way that this has been set up, as we will talk about later. So what type of data traffic is going over these type of channels or for supporting these applications? Well, most of these applications, the Cooperative ITS, Cooperative Intelligent Transport Systems, these applications will rely on two types of traffic: periodic broadcast-to-broadcast communications or event-driven broadcast. So this periodic is broadcast of status messages. And basically, if I'm a vehicle, I transmit my state, that is my position, my velocity, heading, acceleration perhaps, other things about the vehicle, if I'm a bus or a truck or a vehicle, a smaller vehicle, things like that. Something that tells the surrounding of what I am and what I'm doing. So these type of status messages. And in Europe, these are called CAMs. In the US, these are called BSMs. So essentially the same payload, but it's structured in different ways. But that's an upper layer problem. And then we have event-driven broadcast of warning messages. And here's when something, a specific event happens. For instance, I'm emergency braking, right? Then I send out a message, okay, to warn people behind me so that I don't get rear-ended by people not being able to brake in time. So these type of warning messages in Europe is called DENMS. So if you're interested, CAM stands for Cooperative Awareness Message. BSM stands for Basic Safety Message. DEM here stands for Decentralized Environmental Notification Message. I don't know what they were thinking when they designed that acronym, right? But it's sort of, somebody did that and it stuck, right? So we're stuck with this. Okay, so what is meant by broadcast? Broadcast, it means that all nodes simultaneously are receivers and transmitter for this broadcast. So if we think of these 4 vehicles here, what is happening then? Well, this first vehicle is transmitting a message to all the other 4 vehicles. But at the same time, the second vehicle is transmitting to all, and the third is to all, and the fourth to all. So this is the traffic that we would like to support. Now, in Wi-Fi, we need to take turns. So this one needs to start, this one or that one next. I mean, there needs to be some type of ordering of this. Okay, and we will talk a little bit later in the course how this is actually done in Wi-Fi. But essentially, it's like this, that if somebody wants to transmit something, that vehicle listens to the radio channel. If the radio channel is not used at the moment, that message is transmitted. If the radio channel is used at that moment, one waits until it's available again. So that's the main idea. So it's if you want to think of this, it's a listen before talk protocol. And we'll talk more about that later in the course. Now the payload size here is about 400 bytes per message, which includes quite a lot of security overhead. That's why it's a lot of bytes here, even though that the actual data, which is useful here, like position and so forth, is not so many bytes. Repetition rate of the periodic here is in the range of 1 to 10 hertz. So every 100 milliseconds to every second we transmit a new packet. And how often we transmit packets depend a little bit on the channel load, which means that it depends on how much traffic it's in the air. Because if it's a lot of traffic in the air, there is a risk for congestion of the network and data will not get through. So it's decided by that, but it's also decided by the vehicle dynamics. So for instance, a vehicle which is standing still have less need to transmit status messages often, right? Because it doesn't change its state. But if a vehicle is accelerating, switching lanes and braking and things like that, one wants to transmit these updates more often. So it's adapted to that. Okay, any questions so far? No? Okay, so these data traffic models here is basically what we're trying to support in these type of systems with this 11P based systems, or one can also use other radio systems as we see later on, cellular systems in particular. Okay, so if we continue along this data traffic models here, so we talked about ARQ in the course. So these are retransmission protocols which are there in order to get reliability over an unreliable channel. So wireless channels are inherently very unreliable, or are inherently unreliable. So for sure there will be errors occurring in transmission. So the standard way to deal with this in data communications is to use retransmission protocols. However, there's a big problem with this because these are very costly to and difficult to implement if we do broadcast communications. And if we also do broadcast to broadcast where everybody's broadcasting messages to everyone, this becomes quite complicated to implement. And for that reason, ARQ is not used in ITS G5 and DSRC. Okay. So we cannot rely on retransmission protocols to give us reliability. And reliability is something which is important in these applications. So how do we do this? Or what is the implication, first of all, of not using retransmission protocols? Well, it means that the transmitter who transmits a packet does not know exactly who the receivers are, right? Because cars come in and out of radio range. So we don't know this. If I'm the receiver and I transmit the message, I don't know who's out there, right? I don't know which packets these receivers have decoded. Okay, so if I'm a transmitting vehicle, I cannot rely on that my neighborhood has heard my packet. Okay, and this is problematic then, of course, for the traffic safety applications that somehow is relying on that data reaches its destination. So what can we do to get reliability? Well, one way to do is to think a little bit about what the payloads are. So consecutive these status messages, the CAMs and BSM packets, are pretty similar in a way, right? So if I transmit a status message every 100 milliseconds, what does that mean? So what is the speed of a vehicle on a highway, which is in Sweden, say, not on the Autobahn. So it's 90 kilometers per hour. How many meters per second is that? 25, exactly. So 25 meters per second. So 100 milliseconds means what? 2.5 meters, right? So the state I transmit if I travel on a highway speed here and 100 milliseconds later is pretty much the same, right? Okay, I changed 2.5 meters. My position changed 2.5 meters, but my acceleration, my speed vector, and so forth, probably not a whole lot, right? Which means that consecutive messages, the payloads are similar. They're not identical, but they're kind of similar. So occasional packet losses are not disastrous. Okay. So in a way, every packet is not sacred. We can lose a few without compromising the application too much. Of course, it's nice if every packet arrives, but it's not crucial. So basically, we transmit these packets more often than we really need to compensate for the problem of not being able to do a reliable transmission of every single packet. Okay, these warning messages are, as I said, event-driven. So if I'm a vehicle, I'm driving down the highway and I see a moose stepping out and I hit the brakes, right? Then I would like to inform the people behind me I'm braking hard. So I send this warning message, but I don't send it only once. I send it multiple times with a little bit of spacing between these messages. So I repeat the same message many times, and that is done to increase reliability. So if the first packet is lost, maybe the second would arrive and so forth, right? And I keep on sending these until the situation has stopped. So when I don't break anymore, basically. Okay, so this is sort of like a crude way of ensuring enough reliability for the applications to work as they should. Important, however, is that we still have error detection at the receiver. So a receiver that gets a packet which contains bit errors, that packet would be discarded. So the application would never get a bad packet, bad payload. It will get, either it gets a payload and then it's correct, or it doesn't get the payload. So that's nice for the application. The application can actually trust that the payload is actually the payload that was transmitted. So that type of reliability is just that the application cannot rely on getting every packet. Okay, so what are the communication requirements for this? Well, if we have a situation like this, which I described earlier, we would like data from the blue car to reach the red two-wheeler here. And what is what we want from this? We want low delay, relatively low delay, because if the data is ready to be transmitted from here, it needs to reach the destination within a certain time, right? It's not good enough if it's, say, 20 seconds after creation. It's not good enough. So there is a delay requirement here, and it's relatively low, depending, of course, on the situation. What do we need more? We need high reliability in the sense that we would like to guarantee that the packet, the payload here reaches the destination within a reasonable amount of time, with high probability. Now, every packet does not need to go over or have high reliability, but at least one packet should reach the destination within a reasonable time. We need good scalability. We'll talk more about that in the next slide, what that means. And we also need fairness. Okay, and we'll talk about that on the next slide also. And as we will see later on, basically delay and reliability are intimately coupled to each other. So I will talk about that, how to assess that in a second also. Okay, so scalability, what is that? Well, if we're in a situation like this, there's a lot of vehicles here. Okay, and we have 6 megabits per second that we need to share, and all of these vehicles would like to transmit. So what's going to happen is that there is a message coming from this vehicle, say, there is a message coming from that vehicle, for this vehicle, you know, there's a bunch of messages. So actually, traffic congestion of vehicles can lead to data traffic congestion also, right? So a lot of vehicles in the same confined area within radio range of each other compete for the same radio resource, and that resource is limited, and we can run into a problem where not all of this data comes through. Okay, so scalability means that we can support the expected number of vehicles, or not the expected number, but we can support even a situation where it's very dense. Okay, so we want the system to be able to handle this. Fairness has to do with that all of these vehicles get the chance to transmit its packet within a reasonable delay. So we share this. So we are not prioritizing. Rather, we don't want a system where we provide safety for some vehicles but not for all. Okay, it's more reasonable to say, okay, we supply this, some minimum level of safety for everyone, rather than super safety for some and no safety for others. So this is the fairness idea. Okay, and fairness in communications basically means that if we have a bunch of transmitters using the same channel, they should be able to share this on some type of fairness criteria. For instance, maybe the same number of bits per second or something else. Okay, questions so far? No? So let's continue then. So then going back to reliability. So we have here a situation where we have one car, another car, the two applications layers here, application running here, application running here. There's some data that needs to go through this. So it goes down the stack and then over a radio channel and then up like this. Right? Now at the receiver, the medium access control layer here, or actually the data link layer, maybe we should call it, will inspect the frames coming up from the physical layer. If the frames from the physical layer has bit errors in it, which is detected by this CRC or something like that, then it's trashed, right? It's discarded. So from an application point of view, some data goes down here, and some data goes up here. The data that actually goes down here and goes up here is error-free. But some data that goes down here ends up in the trash and it never reaches the application. So from the application point of view, the virtual channel between the cars here is something where we have packet losses. So we lose the whole packet or we don't lose the packet. There is no errors in the packets that arrive, but some packets don't arrive. And there is a certain delay associated with that also. Okay. So this is nice for the application designers because they don't have to worry about the data that comes up to them at the receiving end might be an error. Okay. It might not come, but when it comes, it's not in error. So if we have this perfect error detection, which is a reasonably good assumption, then there will be no erroneous payloads reach the destination application, I would say. Application. With the convention that a packet loss, so what is the packets that are delivered here have some delay because of the processing and communication and so forth. So there will be some delay here. But how do we deal with packet losses? Well, if we say that a packet loss has a delay which is infinite, we can handle both cases. So either a packet has finite delay and then it's delivered, or it has infinite delay, meaning that it's not delivered. Okay, so then we can completely characterize this channel with the delay statistics. Okay. So we can define reliability in terms of the delay statistics. So that's what I said earlier, that reliability and delay are coupled in this sense. They are not two different things. They are actually very tightly coupled. So let's look at that in more detail. We have a transmitter and a receiver like this, and at some point in time, a packet is ready to be transmitted at the transmitter side. Okay, so we have sampled our sensors, we have sampled the frame of data that needs to be transmitted to the other side. What happens then? Well, first of all, there will be a little bit of delay before we can transmit over the radio channel. This has to do with that there are many transmitters sharing the same channel. And sometimes the radio channel is busy, so there might be some waiting time before we actually can transmit the packet. Once the channel is ready, available, then we transmit the packet over the channel. Then there is some processing time at the receiver, and eventually the packet is delivered. Okay, so the time it takes from when it's ready to be transmitted until it's delivered, this is called the latency or delay. So this is the latency for packet number 0. Okay, so what happens with packet number 1? Well, at some point, it's available for being transmitted. There is some waiting time before it goes over the radio channel. It's transmitted over the radio channel, but something bad happens in the radio. Maybe there's a lot of interference, or there is a collision with another packet which is in the air and so forth. So it never reaches the destination. And then we say that the delay for that packet is infinite, right? Because it's never delivered. Okay, then the second and the third packets are happily being transmitted over the channel here. So we see we have some delays here, which are either finite or infinite. And even if they're finite, they're different from time to time because of the state of the channel and other effects, right? So we model these delays as random variables, which have finite varying realizations, and sometimes they're also infinite. So we have a random variable here. And if we can characterize that with its CDF, for instance, we can say something about reliability. Okay, so delay here then. If this is finite, then what does that mean? Well, it means the interpretation of it is the age of the payload at the time of delivery. So at the time of delivery of packet number 0, the delay, tau 0, is how old this packet is, right? It was generated at this time, and now it's delivered, and this is the age of it. And the age of the packet is important in these type of applications, right? So if somebody sends a warning message, one would like to control how old it is when it has arrived, right? Because if there is a fire alarm, for instance, it's not interesting to know that the fire started if the fire started 2 hours ago. It's too late, right, for me to evacuate the building. Same thing for emergency braking here. If I know that the car in front of me has braked, but that happened 2 minutes ago, that information to me is useless, probably at least. Okay, so we would like to control this delay. Another thing that we would like to control is something called the interpacket spacing. So the interpacket spacing here is the time between 2 consecutive delivered messages. So it's the difference between the purple time here and the green time here. So it's the time from the receiver, it's the time between 2 good payloads that we get. Okay. And the interpretation of this, the interpacket spacing here, is the maximal additional aging of the payload before the new packet arrives. At the purple time here, we get a packet which is tau 0 old, tau 0 seconds old. And then as we go along, the age of this packet then increases, of course, as time goes along. And it increases and increases until we get the new packet. And then the old packet is discarded because it's irrelevant now. And the age of the packet just before we get the new packet is tau 0 plus the interpacket spacing. Right? So it's the maximal additional age of this. And this is also a parameter that's important because it tells us the application at the other side, how old is the information that application has. And that is important for these type of traffic safety applications. So any questions about delay in interpacket spacing here? No. Okay. So anyways, one would like to control these things. And these packet drops here that we get, this event, the packet drop here, what is causing it? Well, it's due to noise, interference in the radio channel. There could be a buffer overflows. There could be many different things that makes this not being delivered at all to the application. Okay, and this type of theory here that works pretty well when we do also this repetition scheme that we do in 11p, that we transmit packets many times. Then we can think of this here as being a lot of retransmissions also. Okay. Okay, so there is another interpacket spacing here. So reliability and latency here. So remember now that tau, the delay, is a random variable. It varies from packet to packet. So we can characterize a random variable in terms of its CDF, cumulative distribution function. So if we can calculate the probability that the random variable is less than some value x, and plot that as a function of x, we get the CDF. Right? So then, if we have the CDF, what can we do with that? Well, we see first of all that the CDF is then approaching an asymptotic limit here. It's a non-decreasing function, so it actually increases. It never goes down, right? It always goes up, and that follows from the definition of the CDF. It's a probability, so yeah, so it's increasing in x. At some point, it levels out to a level, and this asymptote here. And the difference between the asymptote and 1 is the probability that the delay is infinite. Okay, so at some point at infinity, it would jump up to 1. Because, well, actually, at infinity, it would jump up to 1. And the difference between the asymptote and 1 here is the probability that the packet has infinite delay, which is the probability that the packet is not arriving at the application. So it's the packet drop probability. So we can read out this number here if we like. If we had the blue curve, we can read out this number. What can we do more here? Well, maybe we have a maximum tolerable delay. Let's call that the deadline. If we had that, we can draw we can then draw this line and then read off the value of the CDF at the deadline. So that's the probability that the delay is less than the deadline, and this is what we call the reliability in this particular setting, right? The reliability we talked about in the course earlier might have another meaning, but this is the reliability in this type of applications. So the application designer has told me as a communication engineer, I would like things to be delivered within this 10 milliseconds, 100 milliseconds, or whatever. And then the communication engineer produces a system which has a certain delay CDF. And for that system, we can read off the reliability. What is the probability that we meet the deadline? And obviously, this needs to be high. That's sort of the meaning between for this deadline. Okay, so deadline, maximum allowed latency, reliability, the probability that the packet is delivered before the deadline. Questions? Okay, so let's continue then. So what are the requirements for this? Well, if one reads the literature, one can say that in general there are strict requirements on the latency or delay. Delay and latency are the same in this context. The latency is not always necessarily low. It depends on the application. For some it's low, for some it's a little bit more relaxed. We need some type of requirements on reliability, and also there is a bunch of security requirements also on authentication and privacy in particular. Confidentiality is not such a big thing here because data which is transmitted is intended for public use, right? It should be readable by everyone. But privacy is an issue, which means that we should not be able to track people as they drive. We should be able to authenticate the information so the information comes from a legitimate transmitter and not from a hacker. We'll talk more about security later in the course. So these requirements, well, there's been some people working on 5G, including myself. And in this project, we put down some requirements on this. So we put the maximum packet error rate at 10 to the minus 5, payload size of 1600 bytes, and maximum latency of 5 milliseconds. I would say that these requirements are quite aggressive, probably not needed. Okay, so it's probably over-designed to do this. So more normal requirements which are floating around in the literature is that maximum packet error probability 10 to the minus 3, 400 bytes, 100 milliseconds. And maybe this is also too much or too little, I don't know. So what I'm trying to say here is that the real requirements are poorly understood. So when you read papers and you read statements, please take them with a grain of salt. Because as far as I know, nobody really knows. And trust me, I've been trying to figure this one out. right? And it's frustrating because it's not so easy to do. And clearly it's also depending on the application. Okay, now going on to $1 million question, I will explain why this is $1 million question. Is that back in the day, the old Greeks, if you had a very important question, should I start a war or whatever, you went to the oracle at Delphi. So this is the oracle at Delphi. So sitting over this, and there's steam coming up, or some with some spirit coming up in her here. And then these people would like to ask a very important question. And the important question here is that, shall we use 11p or cellular for V2X communications? So this is a hot topic at the moment, and highly contested. And then, of course, the oracle here gives an answer to this. The oracle was known to give very ambiguous answers, right? So the answer is, unfortunately, it depends. So this is how I see it at the moment. If you ask somebody who's building 802.11p equipment, what type of answer do you think you will get? Right? And the same applies if you ask Ericsson, who's building this type of equipment. Because there is money in this, right? So again, when you read something, please be careful, right? Who wrote this? And what are their motives? So cellular, for some application, it would do very nicely, because it's there, it has enough coverage and so forth. I will skip this in the interest of saving a little bit of time here. But the new thing about cellular is that in the old day, if we wanted to communicate between two vehicles, even if they were close, we had to communicate up to a base station and down to a base station. This is called uplink, downlink. This gives some delay, right? So the new thing about if we have communication here, in the new versions of the standards, we can communicate directly. So if this is called uplink, if this is called downlink, there is something called a side link nowadays. So this is a fairly new concept in 4G. So it's been standardized in 4G, and it's also standardized for 5G. Not super much in the deployment yet. So this side link here could be either network assisted or autonomous. What is meant by that? But basically, if it's network assistant, it means that the base station is coordinating these transmissions, so making sure that many transmissions, transmitters can share the same radio channel in an effective way, efficient way. However, this should also work in situations where there is no network, for instance, when there is no coverage out in the forest, for instance, and that's called the autonomous mode of this. And then it basically falls back to what Wi-Fi does. It's a listen before talk protocol. Okay, so conclusions. Cooperative Intelligent Transport Systems, CITS applications, rely on this vehicle to anything communication, V2X communication. Data traffic in these type of systems are typically broadcast of relatively small packets. Okay, now broadcast means that ARQ is not very attractive. It's difficult to implement. Okay, so we need to have other means to get reliability. Latency or delay and reliability are important. And you saw how I think they should be related through the latency CDF and reading off the value of the CDF at the deadline to get the reliability. State-of-the-art V2X communications is based on 802.11p, which is basically Wi-Fi. However, there's currently a very big push from the cellular industry to use 4G and or 5G instead for this. And the latest I've seen from this is a legislation from the EU, or suggested legislation from the EU, that one should use both. Like 11p for short range and cellular for long range. At least that. Would sort of make sense, right? But the question is whether there will also be cellular for short range communications. And here, that is still unclear. Has to do with basically what it's a political, commercial, technical issue. And what the outcome of this is, we don't know yet. Okay, so any questions before we end? No? Okay, so then let's stop there and take 15 minutes.